go ahead and get started. Thanks everybody for coming today. Oh, there we go. Should I just start, or are we good? Yeah, all right. So thanks for coming today. I'm going to be talking about deep learning a bit. The goal of this talk is really to have you guys go home and feel like you can experiment with deep learning and start to apply it to some of your projects after maybe doing a little bit of reading on your own when you get home. So I'm going to talk a little bit about myself. My name is Dave Sullivan. I'm CEO of a company called Ersatz Labs. We make a cloud-based platform for working with neural networks in the cloud. I'm at _Dave Sullivan on Twitter if you're into that kind of thing, and if anybody wants to contact me after the talk for praise, criticism, or otherwise, my email address is dave@ersatslabs.com. So I'd like to start with a little bit of history because that's usually a good place to start when discussing neural networks. They've been around for a while. And just so I'm clear, deep learning really is neural networks. Whenever you hear deep learning used in the popular context, it really is neural networks. I would argue neural network research after 2006, which really started focusing on effectively learning deep hierarchies, which I'll be talking about in a minute. But just consider deep learning as neural nets. So the history of neural nets really starts with perceptrons and so-called brain computing back in the 60s. And this was a time when science was kind of in a youthful adolescent period, at least computer science was, where we had first started getting things working. So now it was only a matter of time before we took these perceptrons and programmed them into a computer, and they were talking and walking just like us, and we had robots. And clearly that turned out to not entirely be true. So here were the problems with that. Actually, the main one is they found that these perceptrons were not very representative, capable of learning interesting representations. For example, they weren't able to learn an XOR function, which people, you might often hear, oh, neural networks can't learn an XOR. They can, but perceptrons couldn't, and that was what they were looking at back in the 60s. So people kind of forgot about that. They wrote it off. All right. Then along in the 80s, this thing called backpropagation comes out. And for the first time, they actually had an effective way to train these neural networks. And around the same time, a little bit before, people had also realized, hey, you know what, if we put, and I'll just show you a picture here, if we put a hidden layer, that's the one on the left here, in the middle, suddenly it really improves the representational power, and it can solve things like XORs and interesting things. The problem there was they still didn't know how to get them to work right, how to get them to learn. And that's what backpropagation put into place. So there was this huge burst of excitement around neural networks. And again, everybody was saying, hey, these things are going to get up and start walking around and talking just like us. And that turned out to not be true. So what was the thing that stopped it this time? The thing that stopped it this time was that computers were not very good at the time. So this would have been late 80s, early 90s, really. There was no such thing as GPU computing at that point. People were just trying to get these things to work, and they just couldn't get them fast enough to learn interesting things. And because they couldn't run interesting experiments, they said, these things don't work. Support vector machines are good enough. Let's put all the image recognition stuff on hold, and let's focus on making better recommendations and buying better advertising. So neural networks was pretty much a dead field by 2006. But that was a year when Geoffrey Hinton's lab came out with this idea of unsupervised pre-training followed by supervised fine-tuning. And what this was, here's a really intuitive way of thinking about what this is. It's like taking somebody and putting them in a foreign country where they can't speak the language, right? Immersion. And then leaving them there for like 3 months and then taking them out and having them take a formalized class, all right? Your unsupervised learning is that immersion, right? Is, hey, we're not going to tell you what to look for, and we're just going to start that way. And then it gets the network to a place where it can then give it a better signal, which is going to be your label, and that's going to have it end up in a place that's not a local minimum, basically, or is thought to be more of a global minimum. Now the problem here, the good thing was they suddenly got a lot more accurate, and suddenly they were able to train deep models, which was something that they hadn't really been able to. And deep models have been theorized to be even more powerful of representing interesting things, maybe like image data, maybe learning that information automatically. So that's kind of progressed for the last 8 years, and now it's being actually used in industry, used in production by fairly large companies. So you've got things like GPU computing that have made neural networks very much faster. You've got better methods for training these neural networks. So now people are just saying, hey, give me all your big data that everybody's talking about, and let's train really big models and see how far this can go. And now it's a question of scale. So deep learning is now seeing a lot of rapid advances, both on the industrial side of how are we actually going to use this stuff, as well as the innovation side as far as what are we going to use this stuff for, and what's possible here. So let me just point out the difference between a deep neural network and a non-deep neural network in this context. Non-deep would be on the left, which has one layer of hidden units. The one on the right is a deep neural network, which you'll see has 3 layers of hidden units. These hidden units are just the units in between the input and output. That's it. That is pretty much it. All of these things you hear about with deep learning, all of the GPU computing, all of the fancy methods like dropout and nest drop momentum and all of that, you can use on the one on the left. It's all the same stuff. But the ones on the right have historically been really difficult to use, if not impossible, and only now are really possible, and turns out they work really well and they're being used. Let's skip that. So let's talk about present opportunities and challenges that have kind of been going on the side while all of this has been brewing. So the past 10 to 20 years have created an opportunity. Internet, excuse me. The internet is growing exponentially. So I don't have to tell anybody that 20 years ago, the way we were using the internet was very different. Now we're generating tons and tons more data. You're going to hear that all day at this conference. You've also got compute capacity growing, and you've also got a shifting of compute, where they're actually, Moore's law is slowing down in certain regards, but it's actually sticking to the current pace in others. So this idea of, well, hey, what are we going to use supercomputing for? What are, and where is this going to happen? Is it going to happen on your desktop, or is it going to happen on the internet somewhere, or is it going to happen in your data center in the private cloud or whatever? But compute is becoming a commodity, right? So you think, 10 years out, it really will be a commodity. It'll be traded on commodities exchanges just like corn and orange juice. And that's where this idea of data as a concept is going. Meanwhile, machine learning is really focused on all of that. So the solution here lies in machine learning and understanding data better and being able to discover structure algorithmically without having people look at these problems. It's also more accessible than it's ever been. Never before in the history of time has there been a rush where there is so much value to be gained by the skills, and those skills are so broadly accessible around the world to anybody that can get an internet connection. And that's a new thing. So what are the challenges we're facing now? The first one is scale, and we've got so much data we don't know what to do with it. So you've got different types of scale. You've got long data where it's just so many rows. I've got hundreds of millions of rows of log data, billions of rows, whatever. You've got wide data where it's like genomic data would be a very good example of this, where you have a ton of features, you have very high dimensional feature data, tens of thousands of features, and you have this curse of dimensionality that we're trying to deal with. So deep learning has some ways to deal with that. And then of course you've got this idea of distributed computing versus, do we throw a bunch of GPUs in one computer, or do we throw a bunch of GPUs in one computer and then build like 1,000 of them and hook them up over a network? And it's trade-offs like that. So then you've got this idea of feature engineering, which is, anytime you start with a data problem, it's okay, how am I going to represent this data? And in particular, this has been a real problem in vision, in audio, in so-called rich data, which really is the other challenge. because nobody's really sure how to best represent that. And nobody's really sure, our brain seems to be able to figure it out, but nobody's really sure how that works exactly. Or if that's even the right place to be looking. So then it kind of comes to this larger question, speaking of our brains and an ability to work things out, can data ever be a general concept, right? Are we stuck with this idea of expert systems where if I want to program a computer to trade the stock market, I bring in an expert stock investor, whatever that is, to come in and make those decisions and then programming them into a computer and hope that's not brittle enough to break. Or maybe I'm trying to do face detection. I look at faces and I try to figure out what are the defining characteristics of features. I spend a lot of time on that. Those are two very different people that work on those problems. Then you've got linguists and NLP and so on. But all of this data does seem to have structure. Is there some kind of binding representation, some kind of uniform representation that we can find that describes that? So deep learning comes around, and it actually attacks each of these issues in its own way. So what's attractive about deep learning? Well, first of all, it scales to big data naturally, all right? Because you don't, say you got 100 billion rows of data or whatever, and you want to train a neural network. You don't train on all 100 billion rows at once, right? You break it into what are called mini batches, which, depending on the data, can be anywhere from maybe 2 samples to 2,000, okay? And you work on those batches. So what you do is you say, hey, look at this representative sample. What can I infer about this? Take a step. Okay, give me another representative, take a step. And it does this iteratively, and it arrives at an iterative solution. And it's going to be a different solution every time because you're always starting from a random initialization. So this process is inherently a good way to start to look at scaling this stuff up. Meanwhile, you've got this idea of hierarchical representation learning instead of feature engineering. All right, and this is a slide I stole from NVIDIA. That's their CEO in front at a keynote. But it's a good slide because the first layer here, I'm starting on the left, is the image, right, of a face. And that just goes in raw pixels, right? Then the first layer, it learns, and people always say this, it looks like Gabor filters. All right, over on the left, those are Gabor filters. And this is what the network learns on its own. We never told it anything about Gabor filters. The guy that came up with Gabor filters, I mean, he didn't win a Nobel Prize, but like it was a big deal. And a lot of people use it in vision, and somebody spent a lot of time doing that. And this thing seems to have been able to just figure it out. And while it was doing that, it learned a couple other layers of feature maps that basically take the individual components from the layer before and then use it to construct the next layer up. And then what you end up with, going from looking at these faces to who is this or what is the result here is a lot easier for any decision-making program than if they were looking at those raw pixels and they tried to make that same step, because there's not enough information that's compressed there. It's too general. So this is a really interesting thing, this idea of representation learning. And this is something that is very much on the cutting edge of research, where we're not really sure how far we can take that, or how not far we can take it. But it seems to be a lot farther than people are thinking or thought. There's also biological comparisons to help with the processing of rich data. And another interesting thing, we've got more unlabeled data than labeled data, which is interesting because neural networks can really take advantage of that unlabeled data, kind of that example I used earlier, drop it in a foreign country where it doesn't speak the language. That's the unlabeled data. And then we can give it smaller examples of labeled data. And then there's also this area of research where it turns out that models that I train for one task turn out to be usable for another. So let's talk about...
What did you mean by stochastic addresses?
Yeah, so stochastic mini-batch gradient descent is the name of the algorithm, and the stochasticity refers to the fact that it draws a random mini-batch from the whole distribution each time. So it you get these stochastic mini-batches rather than just iteratively going through it each time. So let's talk about a couple of interesting results with deep learning. These are examples from papers. But but basically this is a, it turns out that if you look at a bunch of image data and give it information about the image, some information, and actually the zero-shot learning is probably a better example. So in this case, you can take Wikipedia and you can generate these what are called feature vectors off of it. And these are word representations that are different than the one-hot encoding that you may be used to, if, kind of standard in NLP. There are these dense representations that the neural network essentially figures out what they should be based on local structure of the word space, essentially. So they start with all of these random, they take every word in your corpus, they initialize them all randomly, and then they iteratively tweak them to, so that words that appear close together end up closer together. And you've got about 50 to 200 dimensions to work with, which is actually a lot of dimensions. Now, what you can think of this as is called feature extraction, and people actually call it this. Is I'm going to extract features from this raw or level data. Meanwhile, you go over to an image problem. All right, you've got an image data set, and you don't have as many labels, but some of them are labeled. And what you do is you generate features off of these images, and what I say by generate features, you end up with kind of the ones over here, right? So I'm going to generate some features of these different images that help me differentiate. Okay. And then, and this is where it's going to be hand wavy, but I encourage you to read the paper because this is actually what happens. They take the words that interact with labels. So you've got the images and you've got some labels like cat, dog, whatever. And then they take this word map that you came up with and they point out cat, they point out dog, they point out the ones that they know, and then it maps it into the same space, into the same model essentially, to where now you can take an image of something that it hasn't seen, like a tiger or something like that, and you can say, hey, convert this over to that shared space and tell me what the words are that are nearest to that place in 50 or 200 dimensional space or whatever. And it turns out to be tiger, for example. And others. And this is this thing called the paper zero-shot learning, which is always, it's almost a joke because it's like, well, wait, so how do I take a label of something when I've got one label and be able to take a vision problem and differentiate between that? Because humans can do that, right? And they can't really, but that's kind of always the goal, is one-shot learning or very few shots. But this is zero-shot learning, and this is crazy, but this is, in my opinion, a really good example of how neural networks can be used to infer really complex relationships. Actually, an even better example of this is, this is mislabeled on the top there, that should be language translation, all right? Basically doing the same thing except with images and text. They take different languages and then map them together based on common words, and then end up with a lot more structure and the ability to build a much better language translation. So what they're doing now is, rather than take words, they're mapping this up into what are called sentence vectors and paragraph vectors, and that's where this research is really going. And what we're going to end up with is really very effective language translation for the first time in human history. Music recommendations, Spotify is actually using the system. There was a great blog post about it based on some work that was done before. But basically this is this idea that, hey, instead of having Pandora come in and hire a bunch of people to hand label all of this stuff, come in and say, okay, this music is really trippy and vocal and this or that. They've got all these different scales that they rate things on. What if you could do that automatically? That really changes the equation a lot. And it turns out that you can. So these recommendation models are based off of just pure audio data, and then reading those using something called a convolutional neural network, and then extracting those features and then grouping those features together. And I should also note that these features, you're seeing it in 2 dimensions. But they start in like 200 dimensions, and then they use a method that's really common within the deep learning community called TSNE. And TSNE is a visualization method that is really good at taking high-dimensional, nonlinear spaces and mapping them into 2 or 3 dimensions. And you end up with visualizations of very high-dimensional spaces that really seem to cluster nicely. So I'm not sure if that's a coincidence and that's what makes deep learning representations look good, or if it's the other way around and just a useful tool to peer into that. But anytime you see people talking about, oh, I've got this huge space, but you're looking at 2 dimensions, TS&E is a really common one that people are using these days. Google was using it to recognize house numbers. This is in production now. They used to have this really complex system that didn't work. They replaced it with a single convolutional neural net, and now they just give it the raw pixels and say what number comes out of this, and it works. So there's actually a talk about that, and a couple of papers have been published. So right, with the now to the practical, and I'm just going to skip to this. So like I said, what I wanted to encourage you guys to do is to be able to go home and try this on stuff that you're working on, all right? So if you have any supervised learning problems, would be a really perfect place to start, where you've got images and you want to pull out either some kind of class, 1 of n, or you want to pull out either a single number in the case of regression or multivariate regression. You want to pull out a variety of numbers. You can do that. And it's actually easier than it sounds to get started. So you might ask, well, what about the parameters? There's a library called Spearmint that uses machine learning to recommend good parameter combinations. So you train one model, that gets a certain loss. It looks at that, it looks at the parameters, it says, okay, try this one. It looks at the result of that. It adjusts its model a little bit. It recommends the next one. So what you do is you train some smaller models, like a lot of them early on, and then you start increasing the size as you hone in on a better parameter space. And that's a really powerful and automatic and smart way to pick parameters and deal with this problem of, well, you've got to be an expert to use deep neural networks. There are open source and commercial solutions now. Open source, you've got Cafe is very fast, is a really good library. PyLearn 2 is a really good one. That's what we use for a lot of the stuff at Ersatz Labs. Torch 7 is one from Jan LeCun's group. He's at Facebook now, so it's actually getting a lot of attention from Facebook and has seen a lot more usage since. IoTaConf 2 is another one that can now do scaling, both model-wise and data-wise. And that's a really interesting one to check out. And then Deep Learning 4J is for you Java folks. And then commercially, there's Ersatz Labs. That's my company. We make software basically for doing deep learning graphically. So you don't really have to do much programming except for the API if you want to build it into your apps once you've trained a model. Clarify is focused on image tagging, but using deep neural networks to do that. Wise.io is focused on like service and text processing. Alchemy API also, but all of us use deep learning and offer that as various services. And then, like I say, never before in the history of time has this information been so broadly accessible. So I'm going to skip that. Questions? All right. Well, thanks.